Greetings, good morning or good afternoon, depending on where you are. We are continuing with our thermodynamics lectures. Today we want to try to develop the boundary layer equation for a fluid flowing on a semi-infinite plane. A fluid flowing for a semi-infinite plane. Now, we are going to base all these discussions on Blazier's model. Now, we are going to look at a two-dimensional flow of a fluid of a semi-infinite plate. I can call it plate or plane. And we are going to use the Blazier's model to develop this concept, to develop this particular concept. And so there will be some similarity with the momentum-based framework which we had looked at earlier on. Remember the momentum-based framework which we had looked earlier on? Just remind ourselves, we had said that U del x plus V del U del y was minus 1 over rho del P del x plus the kinematic viscosity into del 2U del x squared plus del 2U del y squared. The other one which having the y-axis is del y plus V del V del y is equals to minus 1 over rho del P del y plus V del 2V del x squared plus del 2V del y squared. This is the momentum framework. So let's just call it the momentum balance of framework. Let's just call it the momentum framework. So we are going to develop this Blazier's model based on the same framework. Don't forget, rho is density, V is kinematic viscosity. Rho is density. Don't forget those. Don't forget those particular ones. So we want to use this to apply this same model to energy balance and mass balance, or energy transfer and mass transfer models based on this. So using this, applying this, so using the Blazier's model, so applying we want to obtain the energy balance and the mass balance expressions. Just similar to that for the momentum balance which you have there. So in that particular case, we are going to have okay, in that particular case we are going to have V T del x plus U T del x as being equal to K Cp del T squared. Let's work with them the y-axis. Let's work with them the y-axis. Let's forget about the x's. Now, in this particular model, if you remember, and I keep requesting you that it's good to go through the lectures systematically. We talked about this quantity here. We call it the Fourier's number. It was in the Fourier's number, and it was referred to as the thermal diffusivity. It was the thermal diffusivity alpha. So it's part of the Fourier number, and we refer to it as thermal diffusivity. Thermal diffusivity. And so in this particular expression, K is the thermal conductivity. Rho, of course, is the density. And Cp is isobaric heat capacity. Don't forget that. Very important for us to note that. And in terms of mass balance, because when you're talking of energy balance, in other words, we are thinking of the thermal boundary layer, which of course, remember, we had mentioned in terms of thermal boundary layer, we just mentioned that in that particular case, if we have the Prandtl number, PR equals 1.00, then sigma for velocity is the same as sigma for thermal. What was sigma? Let's remind ourselves. What was sigma? Just in case you are lost that point, let's just remind ourselves what was sigma. So this is a diagram which now you should be pretty familiar with. Stream velocity. So we call this the velocity boundary layer. And we have also the thermal boundary layer. Try to get this better so that it at least illustrates what you want. This is the thermal boundary layer. Sigma T, sigma. Now, like we had mentioned, the thermal boundary layer represents those cases where we are talking about the velocity is less than 99% of the upstream velocity. Upstream velocity is approaching the upstream velocity, but they're below 99% of the velocity of the upstream velocity, or what you call far field velocity. And the same with the thermal boundary layer will be the same in terms of the temperatures, in the same manner which we have discussed the velocity. Now, we have seen now this is the energy, for the case of energy. Now, in the case of, so we have said this is thermal diffusivity, don't forget. And so when we are talking, for example, in the momentum framework, our thermal diffusivity there was the kinematic viscosity, which we can call momentum diffusivity. We call it momentum diffusivity. Just in passing, remind ourselves. So in the momentum domain, we can think of this V, which is kinematic viscosity, as momentum diffusivity. So we have now, let's call that momentum balance, energy balance. Then we now want to look at concentration or mass transfer or mass balance. Same way, will be equal to and now that particular quantity there, in terms of mass balance expression here, is the mass diffusivity. And it basically talks of the diffusivity of species A into B. The diffusivity of species A into B. Very, very important for you to remember that. And when you talk of diffusion, remember fixed laws of diffusion are very important. Fixed laws of diffusion. Basically, in a nutshell, in easy term, is simply to say things will move from high concentration to low concentration. Just like we have thermal, when we have thermal transfers, you expect that the differential, which leads to thermal transfer, is movement of heat from high temperatures to low temperatures. High temperatures to low temperatures. So in the same way, fixed laws of diffusion talks about those particular quantities. So when you talk of diffusivity always think of that gradient, thermal gradient, concentration gradient, and the velocity gradient. Always think in terms of those quantities. Now, we have those in our mind. Let me just leave it here. So the boundary conditions for this system, that is that fluid flowing over that semi-infinite plate, the boundary conditions for the fluid flowing over the semi-infinite plate are basically also just based on the momentum balance, and that is, remember, for momentum balance, whereas the suffix xs simply refer to those, whatever the surface property is, that's what the suffix x refer to. And when you're talking of infinity, remember, that talks about the surface property. And we're talking of infinity, we're talking of like the upstream velocity. That's a very far-field property. So, using that, let me just lower it a bit. So we say Vx minus Vs over V infinity minus Vs. That will be Vx over V infinity, which will be Vy over V infinity, and that will be equal to 0. And it is 0 when y? When we are talking about this quantity here, we are talking about it being 0. This particular case, when y is 0. And the boundary condition Vx as Vs, infinity minus Vs, once again, still Vx over V infinity, Vy over V infinity will be equal to 1.00 when y is infinity or x is equals to 0. So what, first of all, before we transpose this to the energy and mass elements, let's just mention something here. Now, let us say that this quantity is 0. I hope you are remembering those expressions there. If this quantity is 0, what does that imply? That implies that Vx minus Vs is equals to 0, or Vx is equals to Vs. That is, we have mentioned this severally now in dealing with the boundary layer derivations and discussions. We have talked about the no-slip condition, which means that when the fluid is flowing, the solid boundary, it's for the no-slip condition, it means its velocity must be 0. So think about it in a very, very simple manner. We have that same infinite plate. What we are saying is that if the two velocities are equal, then it means that whatever the case is, either the semi-infinite plate is stationary, or if it's moving, they're all moving at the same pace, so that the two velocities are equal. So since it is not moving, its velocity is 0, then that of the fluid is 0. And that's the no-slip condition. Always remember that. No-slip condition. Of course, you don't want to deal with the slip condition. It's not intractable, but it's a little bit more interesting. Be a little bit more interesting. Now, using the same basis for the momentum for mass boundary values, for mass boundary conditions. So for the energy boundary conditions, similarly, the energy boundary conditions, I think we can now remove that to create space for ourselves. Let's create space for ourselves. So for the energy boundaries conditions, we now have let's factor them all in now. Energy plus mass boundary conditions. Let us bring them all together, unify them. We have Vx T, and that is C. And once again, conditions are the same. Is 0, y is equals to 0, and is equals to 1, y is equals to infinity, x is equals to 0. So we have just factored that into that particular system. Now, when we compute the shear force or stress between the fluid and the plate, you will find a slightly different expression if we assume that we use a streamline function. If you use streamline equation is very simple. It's just that's a streamline equation. So if you just do a minor rearrangement, then you see that dx u equals to dy v. So dx dy, let's have there dx over dy is equals to v over u. That's displacement. And we have our v, that particular system there. So, I want you just to bear that in mind. So that when we use the streamline equation to compute the shear stress between the fluid flowing on that semi-infinite plate, then tau shear stress now is del v del y, where y is equals to 0. Y is equals to 0, and that will be basically, if we have this particular quantity, what we are saying is that when you do that using the streamline equation, then you'll find that for the momentum-based one, tau will be 0.332 v infinity over x, then square root of Reynolds number. Square root of Reynolds number. Now, I've not spoken much about Reynolds number. We just mentioned it in one of the discussions, one of the lectures, one or two lectures. I think we have mentioned Reynolds number. So let's just remind ourselves what Reynolds number is. So Reynolds number is an important quantity in terms of assessing or developing the flow pattern of a fluid. In other words, it gives you the ratio of the inertial and viscous forces. So important in the assessment of the flow pattern in a fluid. Flow pattern in a fluid. And so basically it gives you the ratio of the inertial forces to the viscous forces. So that the Reynolds number, Re, is simply of a mu. Simply, that is the density and that is the dynamic viscosity. So it gives you a ratio of the inertial and viscous forces involved in that fluid, in that particular fluid, what we call fluid dynamics, whatever the movements are there, it gives you that ratio. So it tells you about the flow pattern, and that is Reynolds number. So that if we extend this to the energy and mass balance systems, then tau will be again 0.332 infinity minus t over x square root of Reynolds number, that is for energy, And for mass, tau will be 0.332 Ca infinity Well, now we want to involve in a very important exercise in looking at this convective heat transfer constants. And so we want to link up the Fourier heat law and Newton's laws of cooling. So we want to use Fourier's heat law interfaced with the Newton's of cooling. And this we have worked with, we have done work now quite extensively with these expressions, and you are familiar with them, and that is Q over A will be minus K del T del Y del T del Y, and this is minus H infinity minus Ts. So remember, we'll just remove the area of flow, otherwise you minus Ka into that, minus H in that, so we have just put it there, so let's get our BQ. And so, putting these quantities into a system, so we have minus K Remember, we already had this particular expression in the ones which you have just cleared up with. So that particular expression, so that will be minus H. Remember, that is the convective constant, heat transfer constant. So we have into H T infinity minus Ts. And of course, we can eliminate, that is Ts, that's Ts. We can eliminate T infinity, Ts here, and we can remove the negative signs. So we have now H as being K that will cancel with that. So we'll have minus will cancel with the minus. So we'll have H is equals to K. Let's have it as 0.332 K Reynolds number, square root of Reynolds number over X. That's a convective heat transfer coefficient, and now you're seeing it in terms of the Reynolds numbers, And like we had already mentioned in some of the earlier lectures, we had said that if Reynolds number PR is equals to 1.00, then the two boundaries coincide. That's the velocity boundary and the thermal boundary coincide. The velocity boundary and the thermal boundary will coincide. Very important for us to always remember that fact. And that is velocity and thermal boundary. But remember, we have also talked about the concentration boundary. Remember, don't forget the concentration boundary, just in case you have forgotten in our earlier lectures, the concentration boundary this was the concentration boundary layer. That was the concentration boundary layer. So, in terms of concentration boundary layer, we'll talk about the Smith number. Being 1.00. That particular point being 1.00. So that in place where you have thermal boundary, now you have the concentration boundary. That's called the Smith. But we hardly use it significantly. You'll see more Prandtl number and Reynolds numbers more than you will see Smith's number. More than you will see Smith's number. And that has to do with the concentration boundary. Concentration boundary. And I repeat, when you're talking of the concentration boundaries, the velocities are below 99% of the far field velocity in the case of velocity boundary layer. Similarly, for the thermal boundary layer and the concentration boundary layer, then those particular quantities, temperature and concentration, are also related in that manner. They are below 99% of those far values.